Hi everybody, today we're going to learn about arguably the greatest sorting algorithm of all time. We're going to learn about QuickSort. Now, there are three things you need to know about QuickSort before we get the details of how it all works. The first thing is, it's as its name implies, QuickSort is really fast. It runs at a snappy big O of n log n time, and it does so for a variety of different inputs. It's not very picky about how the inputs are structured or what needs to be done to make sure you pre-format your items before you throw it to QuickSort. Nope, QuickSort can take anything you throw at it, process it, sort it, and it does so very, very quickly. QuickSort is not a stable sorting algorithm. The relative order of identical items, that order is not guaranteed to be maintained once everything has been put in its sorted place. If you care about stability, QuickSort may not be exactly what you need. But what QuickSort also has going for it though, is it's very space efficient. It's an in-place sorting algorithm where all the sort operations are done on the input itself. We're not creating unnecessary copies of the various data structures in the middle to make the sorting happen, which means it's great from a memory management point of view. Now let's go ahead and dive deeper into how QuickSort actually works in a much more deeper fashion. So the first thing to know about QuickSort is that it's a divide and conquer algorithm, and it's called that because of how it breaks up its work. Now, to help explain this, I'm going to use the example of I'm trying to eat a ginormous cookie. I mean, this cookie is huge. You can see from the size of the elephant, it's a normal size elephant, not a toy small elephant that we see here. It's a really big cookie that, there's no way for me or probably for any other human being to be able to eat it in a very, in one bite, if you wanted to do so. And you might have seen this visual used in my earlier explanation when I talked about recursion, and that is partly by design because the ideas behind recursion and the ideas behind divide and conquer overlap heavily. So I figured I'll reuse that example as opposed to confusing you with yet something else that might be very similar. So the way I can think about eating this cookie is that there's no way I can eat the entire cookie on my own in its current state, which is one gigantic piece, but maybe I can start breaking it down to smaller pieces. So let's say now my cookie is not one giant cookie, but it's now 4 slightly smaller cookies instead. Even at this size, it would be the size of the elephant if we looked at it from earlier. Still pretty big. So let me keep breaking this cookie down into smaller and smaller pieces until it gets probably down to a bite-sized range. So you can see here that a large cookie is now made up of many, many, many smaller sized cookies, and it's very feasible for me to be able to eat a bite-sized version of the cookie instead. Now, the thing to keep in mind is that even though we start with a large cookie and broken into smaller cookies, the quantity or the volume of the cookies we're eating remains the same. The only difference is that the amount is now spread across many cookies. So if my idea is that by breaking into smaller pieces, I'm eating less of the cookie, nope, that is not the case. I'm still eating the exact same amount of cookie. It's just that it's broken up into more bite-sized pieces, which makes it easier for me to quickly process and get through the full cookie itself. So this process of taking something large and breaking it down into ever smaller pieces is how divide and conquer algorithms work. It's core to how they operate. Now, before we go deeper into now how that applies to QuickSort, I just want to take a quick back up a bit and just explain that if you want to learn about data structures and algorithms in JavaScript in a nice beginner-friendly and visual way, my best-selling book, Algorithms, Absolute Beginner's Guide, is just what you need. It's available in digital editions and in physical paper editions at both real-world bookstores and in online bookstores like Amazon. And I have links to all of that below. Now, getting back to our topic at hand. How does our divide and conquer algorithm, QuickSort, how does it actually work? There are 3 steps here. 1, it picks a midpoint value, and this midpoint value is called a pivot. Number 2, it reorders the items based on how large they are relative to the pivot. And in step 3, it repeats steps 1 and 2 on the partially sorted values. So before you might notice that the word pivot comes up quite a bit. So before we dive into the details of how the sorting itself works, let me just talk about pivot first. To help explain how pivots work, I'm going to pick a very contrived example. Here we have a field. This field is made up of 2 types of animals, elephants and giraffes. And what we want to do though is want to make sure the elephants are on one side and the giraffes are on the other side. And the way we're going to determine that is by creating this arbitrary fence, an arbitrary point. We're going to say, you know what, this is the point where we're going to decide which animal goes in which direction. That point is known as the pivot. And so here I am, I picked a pivot point and I placed it somewhat close in the middle of all the items here. And what I'm going to do is specify a condition. All the giraffes go to the left side of the pivot, all the elephants go to the right side of the pivot. And all that remains now is just making sure all the elephants are placed, or not all the elephants, all the animals are placed in their right location relative to where the pivot happens to be. And so once I execute on that wish, you can now see that all the items to the left of our pivot are giraffes, which is exactly what we wanted. All the items to the right of our pivot are elephants, exactly what we wanted. And that really is the idea of what the pivot does. It just creates a moment or a point that we can then rally around to then determine to execute a condition on what needs to happen to the other side of the pivot and what needs to happen to the other side of the pivot. And so now let's shift gears a bit. Instead of talking about elephants and giraffes in the abstract, let's get more specific. Here we have our unsorted list of values, and we want to use QuickSort to sort them. So our values are 4, 10, 7, 3, 5, 12, 40, 1, 33. No real pattern to them, just, I don't know, a nice happy group of values that are completely not in any pattern. And so the first thing we do, step 1 of our 3-step process, is we pick the pivot. And the pivot can be any value in your collection, but for the most part, and how our QuickSort algorithm is going to be implemented, is going to be the midpoint. It's going to be the middle value. So in this case, we have 9 values. So the 5th number is our midpoint. So that also happens to be the value of 5 as well. So that's our pivot. We have 4, 10, 7, and 3, 4 values to the left, 12, 40, 1, and 33, 4 values to the right. So now what we do with our QuickSort is that the way QuickSort works is it takes a pivot value and it specifies that all items to the left of the pivot need to be smaller, all items to the right of the pivot need to be larger. And so if we had to visualize that, that means that what we have right now is, particular pivot, left less than, right greater than. And so what we do next is the equivalent of throwing things over the fence to the other side where the pivot value happens to be the fence. So instead of throwing giraffes and elephants on each of the pivot, we're just throwing values instead. And so when we reorder the values based on the condition of all values to the left of 5 need to be less than, and all values to the right of 5 need to be greater than, we end up with something like this: 1, 4, 3 on the left, 12, 40, 33, 10, and 7 on the right. And so the important detail is that the relative size of the items is now follows the pattern. Less than 5 left, greater than 5 right. That's the first thing to notice. The second thing to notice, and it's actually pretty important, is that these items aren't ordered. They're just smaller, larger relative to the pivot value. It's not, we're saying that 1, 4, and 3 are in its ordered position. No, they're unordered. The only thing that's valid here, the only truth that we have right now is that all the values we see to the left of 5 are going to be less than it. All the values we see to the right of 5 are going to be greater than it. Which then takes us to the next part, which is we have 2 sections of data on either side of our initial pivot that are partially sorted. What we do next is repeat all this pivot picking, step 3, and rearranging on each of these 2 unsorted sections. And the process is no different than we started off with. Instead, earlier we had 9 values that we then had to find the midpoint for. Now we have 2 problems. In this case, the left side, the first problem, we have 3 values. So the pivot is going to be the middle value. On the right side, we have a second problem, in which case the middle value is going to be 33. And so we have 2 sub-problems repeating this whole process again. And so let's just focus on 1, 4, and 3 right now. When we do 1, 4, and 3, 4 is the pivot value, but both the numbers 1 and 3 are less than it, so it gets moved to the other side of 4. We look at 33, similar behavior where you have 10, 7, 40, and 12. 10 and 7 or less, so it goes to the left. 40 is right, 40 is greater, so it goes to the right. And so now you see 12, 10, 7, 33, and 40. And what you can start seeing here is that we now have a large problem that we broke into 2 smaller problems, and now we have a few more smaller problems left. And so we keep repeating all of this pivoting and sorting until we don't have enough values to pick a pivot and divide from, and that happens on our subdivided array has a size of 1. So in this case, we have 1, 3, and 4, and 1 and 3 is our new problem now. We pick the pivot point, which is 3, and then 1 is on the left, and then we continue down. 1 is the only remaining item. There are no more items to pivot from. It is the end of the line for this particular calculation. Similarly, 12, 10, and 7. 10 is the pivot value. 7 goes to the left, 12 goes to the right, and then we have 2 more problems here. 7 and 12 happens to be sorted because, again, last item there. When we look at 40 over here from our first sorting operation, 40 is there's no other items for the sort. It is the pivot. It goes down fully sorted as well. And so once we reach the point where we can divide no further, we're done. And here's an interesting detail. Notice the pivot values we have here: 1, 3, 4, 5, 7, 10, 12, 33, 40. When we read them in order as they appear from left to right, what we'll find is that these are also values that are in their sorted positions. And so reading our pivot values from left to right, the sorted list of values is our sorted version of the array. So 1, 3, 4, 5, 7, 10, 12, 33, 40 is the final answer for our unsorted collection we saw earlier to a sorted version that we saw now. Pretty clever in how it works in terms of how we divide a large problem, broke into smaller problems, and we conquered it, which is the way of saying we asked the question, are you greater than or less than, and we pivoted until we got to just one value that we can no longer divide any further. This is the equivalent of our cookie being small to be bite-sized, but once you go even smaller, it becomes a crumb, and it just all gets all messy. But though, stores do manage to find ways of having cookies that are smaller and smaller. They're still really awesome to eat. So now let's get the performance of QuickSort. We already talked about it. It's a really fast algorithm. You can see in time complexity, both in the average and best cases, it is big O of n log n. Space complexity wise as well, it's really efficient. It's in place, so we're not taking up any more data than what's already available. In fact, we should take up less data. We're often big O of log n. Now, when we look at the worst case scenario, there are situations where QuickSort can be really inefficient. It happens to do with just the arrangement of numbers and how we pick the pivot. So in those cases, the time complexity can be big O of n squared, and the space complexity big O of 1, which is the full size of the actual item itself, which is not ideal in many ways. But those don't happen often. So on average, and in many above average cases as well, QuickSort runs at big O of n log n, and it's considered a really great algorithm, especially for general purpose sorting. It's not very specific on type of data type, or it's not constrained in other ways. So we talked about space in a memory for it being in big O of log n, and it's because it's a recursive algorithm that uses the input itself. And the way you can think about it is that when you go back to the full work we have here, we had an input of 9 values, correct? But notice the depth of the actual calculations here. We have 1, 2, 3, and 4 layers of depth in our calculations, which is approximately the logarithmic value of our input size of 9. And that's the nice thing about QuickSort, is that no matter how large of our items we have here, the amount of calculations we do is not going to be more than log of n, unless in very degenerate cases. And if I want to go further, you can see that if this depth of the tree is log of n, the number of items is n, you multiply that together, you get n log n, which is the actual time it takes to run the calculations itself. So there's an interesting way where the visualization very easily, without having to do any of the complicated mathematical calculations, really lends itself to proving that what we're dealing with is an algorithm of n log n in both time complexity and space complexity of just log n, based on how much calculations need to be done and from a depth and memory point of view. So kind of an interesting way to simplify that. Now, if you want to learn more about how this algorithm is built, there's a lot of JavaScript involved, not a lot, but a fair amount, and it's just hard to describe code on video, and especially if you're watching, you're going to be like, okay, what am I doing? I'm just listening to you talking about JavaScript APIs and methods and names and like that. So the easiest way is just to go to my article on QuickSort on Krupp.com, and you can scroll down, you'll see the full JavaScript and an explanation of how it works. Easiest way is go to Google, type in Krupp and QuickSort, and you'll have the implementation for you right there. Now, the question is probably on your mind, your friends' mind, and if you have any pets in the room, on their minds as well, is QuickSort really the fastest sorting algorithm? The answer is yes. For all general use cases, there isn't a better algorithm out there. Now, the caveat is this. When sorting certain types of data, such as only positive integers, where the range of numbers being sorted isn't very large, sorting algorithms like counting sort or radic sort can run in linear time of big O of n, and they're great at it. And I have other videos where we talk about counting sort and radic sort and why they're as fast as they are and what to watch out for. What are some cases where they won't be that fast. But if you don't have any specific knowledge of the kind of data you'd be having to sort, QuickSort is pretty much a Swiss Army knife, very general purpose. May not be the best at every situation, but for most things, it is going to be really, really good, which that flexibility is far greater than having to special case the sorting algorithm based on your input. And so QuickSort is always considered one of the best sorting algorithms out there. And personally, if I had a tattoo, it would be QuickSort, the greatest sorting algorithm of all time. And so with that, sorting algorithms like QuickSort, they're hard sometimes to understand. They're complicated. And so to learn more about it, and if you have any questions and want to get help from others, go to forum.crypto.com, where others will be very happy to help you out with your quick sorting questions or any other kind of sort that we're running into. And to be notified of new videos I create, hit like, comment, or subscribe. Tell your friends and enemies all about it. Sign up for my newsletter to get updates delivered to your inbox. Follow me at Kurup on Twitter, or X, as they're calling it these days, and for bite-sized updates on interesting things I'm dealing with that are often technology or design related. Lastly, I write more books beyond just the one on algorithms that I talked about earlier. So if you want to learn books on front-end development topics or JavaScript or anything like that, go to check out the link below. I hear they make great gifts, or so they tell me. And with that, I will see you all next time.